And we're gonna start with AD. AD, the floor is yours.
Thank you, Florian, and hello, everyone. I'm very honored to be here. Thank you for taking the time, making the time to sit down with us. And so the purpose of this presentation is something that I meant to do for a long time, basically share some experience. This is all coming from a very much practitioner perspective. Yeah, I'm big on reading books, but I want to always try it out and make sure that things are working before I start disseminating the information. Let me jump. So I've been in the industry for quite a long time, building all kind of interesting platforms. Somehow I find myself on the bleeding edge, cutting edge of technology and business disruption. Currently, I work for Dell. I'm a Chief Technologist for data management, and I'm going to actually have at the end of the presentation, I'm going to have a slide for careers at Dell. It's a very exciting place to be right now in the industry. We're definitely making an impact, and by all means, appreciate if you guys can take a look at the career page and join us. Today's presentation, like I said, is coming from a very practical perspective. Don't expect a lot of algorithms or a lot of white paper type materials. Everything is very practical. Everything is up for discussion. By the way, I don't need to. I don't claim that I know everything. I made a lot of mistakes, but I can always make more. So we're going to start with a primer because I wanted every time I do this presentation, I do this talk. What we learn is actually halfway through the presentation, people are not quite clear what graph models are. So that's why I like to take maybe 20 minutes to do a little bit of a primer. If people feel like they know it, by all means, please feel free to use that time properly. And then we're going to go into modeling exercise, which is going to be the core of the presentation, and hopefully we'll make it today and when I actually can show some code. You've probably seen this before. This is all my personal opinions, not my employers, even future employers. Just because it's practical approach doesn't mean that it's necessarily accurate or reliable. So make your own decisions, make your own observations. Not responsible for any damages. So if you use this code to blow up a nuclear plant or anything like that, I'm not responsible for that. And please don't use this as an endorsement for any technology. Obviously, I'm going to mention technologies and to some extent even companies, but I don't want that to come across as an endorsement. So with that said, probably everyone wonders, why graph data, right? Data represents the world, connected world needs connected data. And what's interesting about this, again, a personal observation, is that we're actually with graph, we're actually moving from describing the world to optimizing the world. And I'm actually going to show some examples on this. Also kind of driving the context. There are multiple types of graphs. And what I would like to make sure that everyone understands that today's presentation is going to be what we call property graphs. Maybe in a future talk, we're going to go into knowledge graphs, but fundamentally today we're talking about property graphs, which are different from the traditional RTF graphs that came together back in 2010. Before we dive into the actual how we do these things, I wanted to take a few minutes to talk about kind of the guiding principles. Right, and the reason this is, I think, would be interesting to people is actually, with this in mind, then we can take a better approach or a clear picture to, how we do data modeling, graph data modeling. So with graphs, as you can imagine, everything is about relationships, right? This is a bit of a departure from traditional, data models. I mean, one can claim that SQL was also about relationships. But using foreign keys and what composite keys to model those relationships can be a little bit cumbersome, and for that reason, graphs is actually the kind of the better solution for modeling relationships. Something that I observed times and times again is actually the value of the data set is actually directly correlated to its dimensionality. And what we mean by dimensionality is actually the connectivity inside the graph, right? How many how many relationships do you have, how rich are these relationships, and that's where dimensionality comes in. I mean, case in point, imagine in that critical moment, how critical it is for the doctor to be able to connect the patient record to medication, to the disease, to a lab work, right? I mean, all these things can also be done with SQL, but with graph, it's actually a lot easier to put all these things together. Use graphs for, I've seen attempts where people actually use graphs to model the system state. Yeah, we can model the system state using graphs, but actually the graphs are better suited for modeling the system behavior. And what that means is that graphs actually can help us determine or define how the knowledge, the information accumulates and transforms over time, right? Yeah, I can model the system state using a graph. How much inventory I have in my data warehouse, or how many cars I have on the road. But fundamentally, using graphs for just modeling the state of the system at that time is a bit overkill. Use it to model the system behavior, and there was how the system evolves over time. Something that became very, very interesting, is actually subject to a lot of academic research right now, is the fact that graphs are inherently complex, right? I mean, you can add only so much, dimensions inside the graph before the whole thing becomes very, very complex. And I had cases when we're talking about 1 billion relationships inside the graph model, right? I mean, imagine the computational power needed to kind of take in 1 billion relationships. So one technique that is being used, and I use it personally, is actually try to cluster, the graph in a way that actually do what in data science is called dimensionality reduction, but has a completely different kind of interpretation, and kind of use that ability to cluster the graph as a way to navigate the graph. And something that this ties back to the system behavior, right? Because essentially what we're trying to do is trying to figure out how the information accumulates and transforms over time, and what that means is actually versioning, right? Having everything the same version is actually going to create a gridlock inside the graph. So you want to be able to version your graph elements that includes the nodes and also the relationships, right? So these are the modeling, the guiding principles in a very practical perspective. Something that I like to highlight is actually the terminology that I'm using, because I'm coming from a system engineering data architecture background, structured data architecture background. I didn't necessarily adopt what they call vertices and edges. I put this in here just so everyone knows that in case you have conversations with graph data purists, right? You don't get lost in translations. I call them nodes just because that's what they call them in, like, say, system engineering and relational data sets. But you can think of if you talk to a graph engineer, chances are they're going to refer to him as vertices and edges. How do you go about? So once we kind of understand kind of the thinking behind the approach. Now, what is the approach? And this is not actually graph specific. This is pretty much the same thing that we've been doing, modeling system behavior and information, transformation, information evolution over time. So define the context, define the information, define what the attributes are, define the relationships inside that, and then use attributes or properties, because we're talking property graphs here, as a way to add additional metadata inside your data set. And I'm using Neo4j quite a bit, but I've seen implementations of GraphDB that actually are pretty powerful. So this is kind of the steps that we're actually going to go into. One thing that I'd like to highlight is that don't try to model the graph as a representation of how the data flows through the system. In other words, I'm in a supply chain implementation. I get data delivered by a supplier. That data has to be cleansed. It has to be structured. It has to be inventory and has to be cataloged. All these things, and then once that data is shows up in some catalog and whatnot, then it has to go into a pipeline, and then it has to go into some business dashboard, right? I mean, it's very, because natively graphs actually have or can implement data flows do not actually use relationships to implement the data flows, because what happens is as soon as you do that first data flow and you learn something about the data, the next data flow is going to be completely different. And at that time, you kind of have to go back and redo your graph data model. So do not use graphs to implement data flows. I don't know if we have. I'm trying to also watch the chat window. I don't know if you have any comments or anything. Any one of you that have thoughts or comments or questions, please feel free to interrupt. Also, kind of turning the contrast all the way up, right? Why a new model, right? How is this different from traditional relational model? And this is this conversation that we're having in especially with the DBAs and traditional kind of data architects, database architects. Why a new model? So this is kind of side by side. How the data will be represented in a SQL format. Although I mean this representation is UML, but this is actually the logical layout that we take and implement in SQL. So you have the foreign keys, you have the constraints and whatnot. And on the right side, you pretty much just have the same representation implemented as a graph. And by the way, the use case here is actually what I'm trying to model is, my data center infrastructure, right? I need to figure out what virtual machines, like here, what virtual machines, sorry, let me see if I can. So what virtual machines runs on what server, and what rack that server is on, right? And what load balancer top of rack switch that rack is hooked up to, right? So this is basically what the use case is. I'm literally trying to model my global data center infrastructure application infrastructure, right? Well, and again you see this 4 keys here, right? Dependencies. Well, same thing actually is represented using a graph. So I have the rack, I have the server, I have the VMs, virtual machines, and then I have the applications, right? The beauty of this model is that it's very intuitive, right? And I will actually show this as a demo. Once you look at this in the Neo4j desktop, intuitively you can tell where things are running. Whereas on the right side, on the left side here, I actually have to write SQL queries and a bunch of inner joins of foreign keys kind of queries to figure out where my virtual machine is running, where if that application database is still operational or not. So that's fundamentally the difference between the two, and this is why graph models are actually winning. Now, taking this to a deeper level, you basically saw what I had as a kind of high level representation with a lot more details, right? And again, this is where graphs are winning, right? Because actually I don't have to create in a traditional SQL, I would have to create another table and link them together, turn normal forms and whatnot. With graphs, I just add, properties, right, inside the nodes. And, if things change, or, I have a new generation of servers or a new application or something completely new, I don't actually have to go back and update any of the previous data. By the way, I put here a little bit of a legend. What are the attributes, what we call them, they call them properties, what are the relationships, labels and nodes. Again, folks, to come up to speed. We are object-oriented programmers, right? Python. This actually is coming up a lot, right? Especially when with the Python developers and Java developers, and to some extent even C# developers. It's like I've been raised in this object-oriented programming world. I've been doing object-oriented programming for 2 decades. None of these things make sense, right? Not graph labels and whatnot. And I mean the mapping is relatively trivial, right? If you actually are willing to accept some limitations. So we're actually mapping labels to object types. One thing that graphs don't do is actually we cannot inherit, right? So if you write a super duper class that a parent class that everyone should inherit, there is no such thing in graphs. But for the most part, is actually pretty straightforward. One thing that our beloved static variables are non-existing in a graph for obvious reasons. They are modeled the system behavior. So nothing is the only constant in system behavior is actually change. So imagine we have static variables; those are probably very counterproductive or useless. So that's why there's an educated decision why we don't have static variables. And then there's the big debate between class and object variables. There is no such thing in graph, again, for obvious reasons, right? So a little bit more background, what graphs are used for. I put here, this is actually, anyone, wanting to become proficient in graph analytics, graph algorithms, please, read this book. I put the link here to Amazon. These are basically the top 3 use cases. This is actually coming from, I want to say Neo4j folks. But essentially, when I said in the beginning that, we're actually moving from, describing the world to optimizing the world, these are the 3 examples of that, right? So just because it's so intuitive to figure out how things tie together, what the influence and the checkpoints are, and how the system may evolve over time, these are the 3 most common use cases. And again, this is from that book. Again, highly recommended. It's time worth spending. One more thing about graphs, right? First thing is we, everybody doing, data architecture, data engineering, data modeling, data operations even, should be painfully familiar with orphan records. In the beginning, when you design the database and you design your data structures, life is good because you have all the relationships and you have all the pointers and you have all the ranges aligned and correlated, and life is good. 2 years down the road, when you have a new DBA architect, or you have a new application, or you have a new customer, or you have a new supplier, chances are the integrity of that model is going to be kind of questionable. And what you end up with actually what we call in the industry called orphan records, where you have this client, let's say client invoice or user record or invoice and whatnot, kind of hanging off of some relationship that is no longer satisfied. Well, that's not the case with graphs, right? Because graphs, the one thing that graphs do really well is actually value the relationship. We talked about modeling system, using graphs to model system behavior. One thing that is good about graphs is actually you don't have to go back and rev all your data attributes or your data objects, your data records every time when you add new data, right? Which, by the way, is not the case with SQL, right? For example, with SQL, if I have to introduce a new attribute in my employee table, I actually have to enter that as a column. Then I have to set some ranges, and then I have to make sure that all the constraints are being satisfied. Well, that is not needed in graph. I can add new data sets, new data attributes, basically completely new data architectures without actually having to go back and rev everything. And this is where I mentioned one of the principle 5 was actually versioning, right? So having a solid versioning strategy for how you actually tag your data actually keeps you on track for the time being and also for the future. Also, because I don't have to along the same line, because I don't have to actually go back and rev anything every time I add new data. What that does actually, I'm instantly backward compatible. Data science is by far the biggest, at least in my mind, is the biggest champion of graph data models. Although I've been in conversations where we're actually looking at using knowledge graphs now to model business knowledge and ontologies. But again, that's something that we probably have to have a separate conversation. We're not going to have the time to discuss that today. And then once you guys see the desktop, is going to the number 5 is going to become pretty obvious that it's actually very intuitive. So that's kind of the preamble, right? Now, if I think about the use of a graph, right? So this is kind of this is just for exercise purposes. So don't take this as now we're getting into investment recommendations and investment strategies and none of that. This is just for simplification purposes, right? But essentially, the use case that I'm trying to illustrate here is, as a investor, banking or institution or VC investor, I need to figure out where I should place my next investor bets, right? And this is what we'll try to illustrate today. So what we're gonna land to is actually something like this. And I know this is I wanted to show you ahead of time because I hope this keep everybody's attention. But fundamentally, this is the result, what the code is going to produce. Basically, what this is showing is actually a clustering of different technologies, right? And based on how many relationships exist to that technology. So you see 5G here, right, being central point of many other smaller technologies and also small research. But fundamentally, if I were to be an investing banker, once I see this data, this will actually give me an idea that, hey, 5G is probably the next technology that we need to invest in. And so this is basically for the the bell curve, but also there are some outliers. I don't have that on the screen here, but you kind of see some of the outliers, and that can actually that's where potential disruption can come from. So essentially, this is what the code is going to be. So again, to reiterate a use case, I'm a VC investor. I'm looking for my next opportunity to invest, and I need to look at data and use some technology to turn that into something that gives me an idea, where I should be heading, right? So that's the use case. This is what we're going to produce. I'm going to actually get very practical here, very pragmatic. So what I'm going to use as an input data set, I actually picked the IEEE publications, data set. It's got about 10,000 records at the last count. Obviously, I didn't take all 10,000, but this is just for illustrative purposes. I picked the 100 records, and this is what IEEE is publishing about their publications, right? The actual JSON is quite long. Again, I took just a screenshot here, so this is not actually the whole record. We're gonna look at the code and you're gonna see it. But fundamentally, this is what the input data look like, right? So now think from a investor, VC investor perspective, right? I look at this JSON, it makes complete no sense, right? How am I supposed to figure out, that 5G is the technology that I should invest in, right? So the first thing that, as a data engineer, data practitioner, we have to do by looking at this data, we have to figure out what are my nodes, right? What are the data records per se, right? And by looking at this, I can tell that this JSON attributes here can be a node. I also have the publication. The publication JSON is much longer. I don't have everything on the screen, but you can read here, right? So I kind of have, and I have to have a second node for the publication, right? And this is again very intuitive. An author publishes a publication. The publication has an author, so no brainer so far. But in the process of analyzing taking this analysis, we actually observed that there is actually a piece of the JSON record that kind of wondering, if we follow first and second principle, it's still not clear whether this should be another node or should be just properties to existing nodes, right? And the conversation, this actually happened. The conversation went, hey, if we make it an independent node, right, our analytics are going to be much easier, right? Because I don't have to pull as many relationships. I basically don't have to walk the graph as much, right? If I have to add another attribute, I can actually add it quite easily, another property, right? It's much better observability because the graph itself is smaller, right? But again, the problem that we're having is actually, with that much information packed into each of the nodes, we're actually going to see, graphs that are a lot more complex, right? And again, this is actually not unexpected. Now, if you think about, I'm going to add all these attributes to existing nodes. So I'm adding the attributes to the property to the publication node. I'm going to add the same attribute to the author node. this is actually something I've seen this happening from doing this from people that are actually coming from a SQL background, because this is exactly how SQL engineers are thinking about structuring the data, right? So I can have columns that I can have tables that can have 1,000 columns, right? Nothing wrong with that. So and also to some extent the object-oriented programming folks kind of taking the same approach, because what happens is that I don't have to get too many records. I don't have to associate too many arrays in my code. But at the end of the day, what that does is actually now I really have to spend a lot of time refining my analytics, because at the end of the day, what you have to do with this kind of model is actually do the equivalent of a select star, basically dump the entire table, right? And then figure out, which of these columns, which of these attributes you need, right? It inherently makes the data exploration much more difficult. So, any thoughts? If you look at this, any thoughts? What you think the right approach should be? So this is where that effort actually went. After quite a heated conversations between the two camps, the decision actually go into make them independent nodes, right? And this is actually helping us with the relationships, right? Because the relationships actually drive the hierarchies, and we're going to get to that in a second here, right? And then as we said in the beginning, one of the principles actually do not embed too much information into your node, because what happens is that node becomes quite heavy, and every time when you need to add a new node or you need to kind of extrapolate that structure into something else, things can get very difficult. So keep him very, very light, very lean. Use relationships and to model these behaviors, right? So that was all good. So now we have three nodes. We have author, we have a publication, and we have a term, right? The next step is actually to figure out, okay, life is good, but is there something else that I'm missing, right? Because one thing that we want to do is actually, in the process of transforming this, the original JSON, into a graph, is actually not to lose the resolution. In other words, we don't want to end up with a low resolution, data set, right? And personally, I use this library called JSON. Right, and what this thing is actually doing a classification of the schema, and it's telling me some interesting aspects. For example, these are some of the attributes that you have to consider, right? And it's up to you to consider or not. But if you really want to maintain the high precision aspect of the original data, you better pay attention to this. So using JSON actually is gonna help you quite a bit. And that actually turned out to be another, based on this analysis, that turned out to be another node here. So this is what the data model looked like, right? So we had, based on that exercise, we had the author, we had the publication, we had the ISBN. This was the result of the JSON analysis. And then, a comparison between, attributes and nodes. Basically, we have a third term here, right? So this should be relatively decent, and this is actually a good starting point. One thing that actually became quite obvious is that because some of the relationships are actually going to be used into deep analytics of the graph, try to use unique names. In other words, if you have, ID here, right? ID here and ID here, right? That is going to make those analytics extremely complex. So try to use unique names for the relationships and the attributes, and make sure that you understand that relationships are unidirectional. So, like I said, this was relatively decent, right? One thing that it was asked is like, well, as a VC, I definitely understand that this is actually going to help me with the technology, but also I want to understand what are the think tanks, what are the research centers, right? And we had this, incidentally, we had this thing called affiliation stuck under the author, and the recommendation was actually, hey, we need to actually pull that out, because it's likely that multiple researchers are going to work for the same university or for the same research center. So this, again, from an investment perspective, this is also going to be interesting to know what projects to fund, what are the pioneers. So this is basically the model that this exercise had produced. So to recap, right? I wanted to put this because we went to about dozen slides. I wanted to put this on one slide to kind of give everyone the roadmap, right, for how you go about taking. I don't want to say any data set, but JSON data sets are pretty straightforward into a graph. So the first thing is inspect the data sets, try to extract some of the features. I use JSON vectorizer quite a bit. Data path in few instances, but not a whole lot. Get into kind of switch into a kind of the graph universe, and network X is actually helping a lot. I don't know if you have people in the audience who actually been using network X. I'd like to hear other people's input. I'm very happy with what that the library can do, and then deploy and visualize. One thing that I like to highlight is that this is actually a cyclical process, right? You realize, just like we looked at the data set, and we realized that actually we need more features, right? So there is going to be a feedback loop, right? And sometimes that feedback loop is relatively incremental, sequential, but sometimes, like when the VC investor doesn't see what they need on the dashboard, sometimes we kind of have to skip and go back and regenerate some of the features, or generate brand new features, and then kind of take it from there. That's kind of what the presentation was about. Let me switch to, hold on. Let me switch to, sorry for this. Oops, described. Okay, so what I have here, right? I have the Neo4j desktop. I probably have the dashboard somewhere too, but let's see. No, it doesn't come up. You have to trust me. This is the Neo4j desktop. So if I try to run, this is those of you who are not familiar with the language, it's called Cyber. If you go to the Neo4j site, they actually done an awesome job, documenting and providing a lot of examples and use cases, and there is actually a relatively large community around Cyber. So it would be good to at least understand, the query language, and because that's actually going to explain some of this relationship stuff. So again, nothing here. Oops, sorry. So the code that does this thing, right? It's actually, free, plain vanilla, right? I'm not going to go a lot of details. The actual, just JSON is here. Again, sorry for this. I took only 100 records. I didn't actually. The original data set is much larger, about 10,000 records. But I took 100 records here, right? And all I'm doing is just processing, parse the JSON, find the different attributes, build some data classes, and then down here, this is basically when I write the data to the database, right? Again, pretty straightforward. About 200 and some lines is not that big of a deal. I don't claim to be an expert in Python. I learned Python because it definitely was a lot more productive than Java and C#. Been doing Python for maybe 15 years. I don't claim to be an expert though. But this is basically what that code does. So let's Let's run it. Oh, someone had a question. I'm sorry. Andrew, go ahead and ask your question, please.
It was, is there a one-to-one mapping from a graph to SQL database?
No. No, there is none. At least in my experience, I haven't come across one. I'm sure some smart guy will probably write some kind of compiler or interpreter, if you will. But so far, I haven't seen. The reason I'm saying that I just saw an article the other day that actually someone wrote an interpreter for SQL to run on NoSQL databases, and it's literally just that, an interpreter. But again, I haven't come across one, and I mean it would be a big challenge, would be a big departure, because with SQL, relational integrity is key, and is based on foreign keys and constraints and and indexes, which is not the case here, right? Here I can have the same. I can have two versions of the same object in the database, and everything would work just fine.
Yeah.
Does that make sense?
Yeah.
Yeah. This is I hope this is a beginning of a bigger conversation. I would love for us to for the Austin community to become very proficient in graph, because there are lots of companies that are actually exploring this and turning this into business opportunities. So it'd be good for us, the technical community, to become extremely proficient, and to some extent even disrupt the research and the prioritization. Yeah, there are so many, and that's why this is kind of the very, very basic, if you will, to some extent fundamental, but the real challenge, the real exciting part, at least to me, is actually knowledge graphs. And that's where I see a lot of especially academic research going. I haven't seen that many VCs investing in those kind of companies, but there are people in town that are actually very very proficient in knowledge graphs, and it is coming up a lot. Businesses are coming to the realization that there has to be a better data architecture than traditional SQL data warehouses to represent information and knowledge, and knowledge graphs seem to be that pinnacle. Again, there is a lot of hype also, as we've seen before, so it doesn't mean that it's going to be completely deterministic. Only future would tell, but knowledge graph is probably where we need to become very proficient, very knowledgeable. So okay, so this thing had run. Let's go back to the Neo4j, run that command again. And I'm not doing, you're going to see actually, I'm sorry, this is the, I'm not, there are ways to actually optimize the clustering inside the graph. You're going to see actually nodes gravitating kind of together. I actually left everything to default, but I'm being told that there are actually ways to actually do this, clustering, customize this, and also add weights to everything. There are also ways to add weights in the relationship. So this whole thing can become a lot more meaningful. But this is basically the database, optimizing. Remember when I said, graphs are all about optimizing the world? This is actually in action. So you see, all the nodes kind of, gravitating and being defined. Once this thing settles a little bit, I'm not running on a very powerful machine here, so that's why this is taking a little longer. But you start seeing, a bit of clustering already, right? So 5G is already becoming, very popular, right? And you see these other, clusters that are forming, right? Fast, I don't know what that fast convolution filter, OFDM, new radio, clipping. So 5G is definitely again, this is a subset. So I suspect the first 100 publications, 100 records in that data set had 5G in it. So that's why, but if you kind of grab the bigger data set, chances are this graph is going to look, quite different. So this is basically, the power of graph in action. So, you see that it's already very intuitive. I don't have to build, a super duper, dashboard, or I don't have to have pre-colors, or I don't have to have, MicroStrategy or Tableau or one of these, more sophisticated, dashboards. I can already tell here. I can turn this over to a VC investor and say, look, this is what the technologies are. This is kind of how they are trending. You can take it from here. So, and everything was done, like I said, with about 200 lines of code. I'm sure you guys can write better code than I do. So that's probably going to cut down to 100 lines or less. But fundamentally, this is the power of graph. Right. We'll let this set a little bit more, and then we kind of have to move on. I don't think I can show the outliers here, but if you move this, let me see. This is gonna no.
So is this like, is there like right now, like it's all like, if you were to analyze the data, it's all visual. Is there like another way to kind of get like a number of connections and anything like that?
Yeah. Those are the three algorithms the three types of algorithms that I mentioned, right? So if you go back, yeah, that's another opportunity for investments, is actually graph analytics, right? So these are actually the algorithms. I don't have the book here, I can show you, but there are actually plenty of details on what kind of algorithms, and how do you actually apply those kind of algorithms, because they are somewhat different from it. I don't want to emphasize, machine learning and neural networks and deep learning and all that, but you're actually going to see with graph analytics, some of these algorithms can actually take advantage of the dimensionality, right? Well, as opposed to traditional, and I don't want to sound trivial, but traditional machine learning models where the data set is basically the training data set is basically a flat JSON. Again, highly recommend the book if you guys want to get into this. So this is so it's again, we see some gravitational force, right? Gravitational waves to use the another term. So we see a gravitational force here, gravitational pull, but also there are some outliers. So if you were to look at this and say, well, I understand that 5G is the next technology to invest in, but 3 years from now, what are the next technologies? Then you kind of see these are actually a lot more dispersed, and one can do a Euclidean distance on some of them to basically get a better quality cluster. But again, this is what, again, very intuitively, I wrote 200 lines of code. I picked a public data set, and I can produce this kind of insights. I don't think personally, I mean, I've been in the industry for a long time. We never had it this easy, right? We always had to go and pick, God knows what dashboard, re-architect the data model to feed the dashboard, transform the dashboard, transform the data to feed the data model that the dashboard expects. Here it's a lot faster. And if I had a better machine, I'm probably gonna be able to show you even more stuff. But again, this is the power of graph. Now let's see where this takes us.
So before we move on, do you mind if I ask you a question?
Yes, sir.
So we have a question from Sherry here in the chat who would like to ask, in your demo, what is the criteria for cluster?
Oh, as I said, this is
how to point to a node.
Yeah. So, like I said, I didn't actually. This is all default settings in the Neo4j desktop. I didn't do actually any of the clustering myself, right? So this is basically what Neo4j desktop is doing, right? I didn't do myself. I can go in and add my own clustering algorithm, and I can actually add weights, and I can show these things popping up even more. But in this particular demo, just because I want to leave everything to default and kind of concentrate on the use case, I didn't actually do any kind of gravitational pull or any distance calculations.
Awesome. Thank you so much for that answer.
Yeah, this is, again, for the purpose of this conversation, I wanted to be more kind of visual and illustrative. We can go and add propagation algorithms, and there is another one, influencing algorithms, basically to figure out what previous conditions are going to create opportunities for the next system state or the system behavior. Those are definitely very interesting conversations, and that's where it kind of starts also crossing into knowledge graphs. But again, for the purpose of the conversation, I wanted to keep it relatively fundamental, if you will. Again, more than happy to continue the conversations on email or chat and whatnot, maybe future talk. But again, this is an introduction. Any other questions? I think, Florine, how much more time I have? I have 9 minutes, right? 10.
Don't worry about the time.
Yeah, don't worry too much.
Okay.
I have a question about the libraries. You showed like 4 libraries, JSON and several others. Which ones are you using here?
In the actual code, I use JSON. Right.
Okay, so this is only JSON.
Yeah,
you have
but
like 3 more libraries there.
Yeah, I didn't, again, for the purpose of this, let me put this up again. For the purpose of this dialogue, I actually didn't want to confuse you guys with the other 3, right? But so JSON was the one that I used to for this conversation here. So the first step was to actually identify some people call it the primary nodes. So these 3 nodes here, right? And then the conversation became about, by going with this model, right? Because I'm not going to be able to put every single attribute in my graph, right? So by going with this model, is there anything that we're actually losing? That's why I said, we're actually lowering the resolution of what we're producing, because that's not what we want to do. We want to maintain the high resolution of the data when you transform the data into the graph, right? And this is where JSON came in, right? So basically, what this thing did, actually look at my JSON schema, right? Because it's difficult to read that schema, from here. So JSON actually went only after the schema, and JSON actually identified additional schema attributes that were not actually initially considered. Right, so this is where JSON was used, and the end result of this is actually we produced another node type. We call it ISBN, right? So this is all basically the result of using JSON. I didn't show you guys how to use JSON vectorizer. This is another very powerful one. If JSON is producing too much data, back to the schema analysis and schema output, JSON vectorizer is actually the next one that we should be using, right? And then network X. This was the one that I used in absence of the Neo4j desktop, because I didn't want to, as you can see, it's quite slow and it's quite time consuming. So I didn't want to use Neo4j desktop for every single iteration of my schema, right? So when we went from this the first version of the schema to the second version of the schema, the way actually I represented that was with network X, right? And this is producing a little bit more than, you can turn that into a JPEG, if you will, and you can put that into your article or your white paper, if you will. So this is basically the whole roadmap or the steps. For this demo, I used only this one.
Okay, nice. We'll have to bring you more for the others.
Please. Yeah. Okay, any other questions? No? Okay, so as I mentioned in the beginning, Dell is a great company. We definitely creating a lot of disruption in the market. We have a lot of pioneers, forward thinkers. We have about 1,500 positions open, technical positions open. I could not put everything here, but I put my email address there, my work email address. If you have any questions or you need a better understanding kind of how to navigate, because it can be a bit confusing, just drop me a note. And otherwise, feel free to reach me on email, ad.rationalintelligence@gmail, or Rational Intelligence is my site. With that said, thank you very much for your time, and I sure hope we take this into a very interesting conversations.
All right, well, thank you so much.
Yeah.
Yeah, we'll definitely have you again. And you got me excited about the graphs. I'll definitely read that book. Cool.
Yeah, if you guys, I mean, they are I don't want to endorse anybody, but they are folks from data.world here in Austin, and they are a bunch of startups, and I'm actually having conversations with lots of people, and there is a lot of excitement around this. But there are people that are more proficient than me on graph, people that been doing down this path and been working with actual real use cases, business use cases. So we should probably look into also getting those folks.
Yeah, that should be.
So actually, data.world talking about it, we're talking to them.
Oh, cool.
Yeah, we've been talking to them for a while. They've been in Austin for a while, but talk takes time.
Let me know if I can help.